Today we want to go on to the next section on definite integrals. Now, before we really get into definite integrals, we want to look at the limit of a Riemann sum. And this is really what this video is really about. What is a Riemann sum? And then how do we find the limit of a Riemann sum? And then at the end, we'll connect this to what a definite integral is in terms of a Riemann sum. Now, if we look back to what we looked at last time, we talked about the RAM rule, or the rectangular approximation method, for a way as estimating the area underneath of the curve. And we looked at three types. We had a left hand, a right hand, and a midpoint, and we did some of these by hand. We calculated the distance traveled with velocities of a car, and many times we just used the program on our calculator to find this. So if you remember what we were looking at, if we look at one rectangle, if we have a specific rectangle that we're trying to find the area of this rectangle, and this would be a left-hand rectangular approximation because we're using the C to give us our functional value. So the area of this rectangle would be our functional value, f of c, that is our height of this rectangle, times the width of this rectangle. And in this notation, the general kind of with variables, that would be d minus c. So this would be the area of this rectangle. And if we were approximating this area by more subintervals, we could maybe, make some more rectangles and so forth. But for this one rectangle, this is what the area would be. And what we want to do today is expand on that to the idea of a Riemann sum. So the first thing we're going to talk about is a partition. And a partition is just a way of dividing up that subinterval. So let's say we have this subinterval from A to B that we're looking to integrate or to find the Riemann sum of. Now, let me go back and look at an example of one we looked at previously. Well, the one we looked at previously, we had 4 subintervals, n was 4, and it was from 0 to 2. And we broke it into 1, 2, 3, 4 subintervals. So in this notation, this x sub 0 is our first point, x sub 4 is our fourth, and then we would have x1, x2, x3. So it goes from 0 to 4. The reason we start on 0 is so if we have 4 subintervals, n is 4, our final value is x sub 4. So if we look at that as a general case, this is our x sub 0, this is our x sub n. We don't know how many we have here. And so it starts off as x sub 1, x sub 2, x sub 3, x sub 4 for all of our subintervals. As you get to the end, this is x sub n. The one right before that is x sub n minus 1. And in the general, just a spot in the middle here, the notation we're going to use is we're going to call this x sub k, meaning some just general spot in the middle. The one right after that is x sub k plus 1, and the one before that is x sub k minus 1, just to get some notation done. Now, one of the things that you will notice is different than before. Here, each of our subintervals was equal to a half. They were all the same. Here, that's not necessarily going to be true. It could be in spots, but if we look here, these two values are much closer than these two values. And that can really help us as we look at more difficult problems. If you look at something like this, in this part where the slope of the curve is very steep, you may want a whole bunch of really small rectangles to get the best approximation you need. And that's a lot of calculations. But if there's somewhere over here where you could use one big rectangle to get a really good approximation, that would also make your life easy. So we want to have the option of being able to split them up and sometimes put them really close together and sometimes make the width of our rectangle much further apart. Okay, so let's imagine we have this graph and we have this subinterval x sub 0, 2, 3, 4, 2, 4. Now, instead of just saying right, left, or midpoint, what we want to look at is we want to look at something where we take an arbitrary c just somewhere in that subinterval. So let's just say right here, C. And this one right here. So in every subinterval, we just pick some C. Now, we're not going to worry about if it could be left, could be right, could be midpoint, because as we're going to get into this more, our width of our subintervals are going to get smaller and smaller. So as they get smaller and smaller, the value of the C moving around doesn't affect us much because the subinterval is really small. Now, what you'll notice is this first subinterval from x sub 0 to x sub 1, this is our C sub 1, because that's the first subinterval. This is my C sub 2. This is my C sub 3. This is my C sub 4. That's what the CK means, just picking it for some arbitrary value in that subinterval. Now, if we look at each of these and we want to look at our rectangle, so we go to my height would be here, and then this rectangle would come up like that. This value is here, so my rectangle is like that. This value is here, so here is my rectangle. So you see, by letting each rectangle kind of pick its own value, we can actually do a much better job of getting a better approximation. So then we have our first, our second, and our third and fourth rectangles. Now let's talk about the area of each of these. If we look at the first one, the height of this rectangle is f of C1. So the area of that first rectangle is f of C1 x1 minus x sub 0. That's just like we started with today, going back to here, of how we found the area of that rectangle. But now we can generalize it for all of these. And then for our second subinterval, it would be f of C2 x2 minus x1, f of C3 x3 minus x2, and then f of C4 x4 minus x3. So there would be all of these rectangles. Now you'll notice they follow a very regular pattern here. And we can actually think about this where this number right here, that is just the width of this rectangle. That's the differences in the x. So we are going to write this even in a shorter notation and saying that x1 minus x sub 0, we're going to say is delta x1. This is the functional value. This is the height of our rectangle. This is the width of our rectangle. Plus f of C2 delta x2 plus f of C3 delta x3 plus f of C4 delta x4. Now, if you notice what we have, there are four things. We could write this as a sigma notation of k equals 1 to 4 of f of ck delta xk. So we are able to take this rectangular approximation method and using the width and the functional value, and we end up with the sigma notation. And that sigma notation is our Riemann sum for n subintervals. Here we did it for 4. But really, we could change this to any number we wanted to, and that just adds more terms. Now, the math would be hard to figure out necessarily, but we're just kind of doing this in general here. So I could make this n anything I want, and that is the definition of what a Riemann sum. This right here is the height of each of these rectangles, and this right here is the width of each of these rectangles. So this represents the area of each rectangle. That is our Riemann sum. And as we've kind of hinted at before, if we want to take this Riemann sum and we let this n get bigger and bigger and bigger, our sum gets closer and closer to the true value. So what we can do is we can take the limit of this Riemann sum as n goes to infinity. So that means as we get infinite number of rectangles, each subinterval gets infinitely small. That's why our c sub k doesn't matter, because our subintervals get so small as we get an infinite number of them that it doesn't really matter if you're left, right, center. It's going to be basically the same value because you get an infinite number of them. And we call what this is equal to, the sum of this infinite series, as our definite integral. So we want to find the limit of this Riemann sum gives us this definite integral. This is not an approximation. This is the actual value. This is the exact value that we're able to find. Now, let's kind of look at an example. And this slide kind of has it very abstractly, so I want to look at this, and then we'll break it down more kind of concretely, and then we'll come back to this in a second. So let's talk about the subinterval part. So we want to look at from 1 minus x squared on 0 to 1. So let's talk about the subintervals. First, I want you to think about what we've already looked at. So let's say we're looking at a subinterval from 0 to 1, and n is 2. Well, we'd have two subintervals from x sub 0 to x sub 1, and x sub 1 to 1. And I want you to think of 1 as 2 over 2. Now, let's say we increase our n, and I'm going to increase by a factor of 2 because it makes the math easy and the picture easy to see. Let's say we're going to go to 4 subintervals. So this is x sub 0. We put our 4 lines. We get x sub 1, x sub 2, x sub 3, x sub 4. And this would be 1/4. This would be 2/4, and I'm writing it that way instead of simplifying it so you can see a pattern here. This would be 3/4, and this would be 4/4. Now, if we do it one more time, let's go to 8. So we do the same thing. From 1 to 0. We divide this again. This would be x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, x sub 8. Now, if we fill these values in, this would be 1/8, 2/8, 3/8. And notice the numerator for each of these is the same as the x sub whatever on the bottom. So 1 is 8/8. So x sub 4 to x sub 5, this subinterval is 5/8 to 4/8. That right there is what back here they have in this general notation. So you can see here that this general notation for n is showing what we have on the right. If n is 2, it would be 0 to 1/2, 1/2 to 2 over 2. There's your 2. If your n is 4, it would be 0 to 1/4, 1/4 to 2/4, 2/4 to 3/4, and then 3/4 to 4/4. If n is 8, it's 0 to 1/8, 1/8 to 2/8, 2/8 to 3/8, and so forth. So this is just a general way of writing this for any value of n. And you could write that for 3, 11, 15. Just, it makes it easy with the numbers I chose. Now, if we think about each of these, in this case, we're just making it simple right here. Each of our subintervals is equal to 1/8, and they're all equal. So for each of these, we're going to have the functional value, which is our height, times this 1 over n, which is our width, to give us our area of our rectangle. And if we add all those up, that is going to be our Riemann sum. So let's look at doing one of these Riemann sums with this problem. So to get us started, we're going to have two formulas that we're going to use. Our first formula is delta xk, and if you think about our formula, let me write it here for our integral is the limit as n goes to infinity of sigma k equals 1 to n of f of c sub k delta xk. So you can see the two things that we need. We have our f of x, we need our c sub k, and we need our delta xk. So first off, our delta xk is going to be b minus a over n. And remember, this is our a, this is our b. So that is going to be 1 minus 0 over n. That's 1 over n. So we're leaving n in our equations. Now c sub k, a is 0. So that's 0 plus k delta xk, which is 1 over n, which gives us just k over n. So now we can plug all of this into our definite integral, or the limit of our Riemann sum. So this is the limit as n goes to infinity of sigma k equals 1 to n. We get f of ck. So that's going to be f of k over n. So that is going to be 1 minus k over n squared. I'm just putting this c sub k in there, times delta xk, which is 1 over n. And I think you can see this should look very, very similar to the problems we did last week on our homework. Finding the limit of a sigma. And we're going to do the same thing by using our formulas. So if you remember how we did this, the first thing I'm going to do is I'm going to pull out the 1 over n. I'm going to break this sigma into two parts. I first get the sigma of 1 minus the second part. I'm going to pull out the 1 over n squared, and I get the sigma of k equals 1 over n of k squared. Now, we use our formulas. The limit as n goes to infinity. And the first one, now remember I have to distribute this back through when I use the formulas. The formula for just 1 is n. So this is 1 over n times n. Minus, once again, 1 over n times 1 over n squared is 1 over n cubed. And my formula for k squared is 2n cubed plus 3n squared plus n all over 6. Now, if we simplify this, these cancel, and I get just 1. And if I look at my leading coefficients here, I get 2 over 3, or 2 over 6, which is 1/3. So my answer is 2/3. And this is not an approximation. This is not, a approximation of the area under the curve for this function on this subinterval. Now, I do not have my calculator here to be able to bring this up, but if you would go in to our estimate or RAM rule that we looked at last week, and you would make this your functional value, you make this your A and your B, and then make your N 10, 20, 30, and run that approximation for the left, the right, and the midpoint, you will see, you will get numbers really, really close to 2/3, 0.66666 repeating. Now, there'll be approximations. You won't get exactly 2/3. This is not an approximation. We are looking at the limit as n goes to infinity. We are summing up an infinite number of rectangles. This is the definite integral. This is the exact answer when we take this limit of this Riemann sum. Now, instead of having to write this out as this long limit notation, we kind of have a shorthand that we like to write this as. And we write it as this definite integral right here. So let's talk about how these are connected. First off, this f of ck, that's the functional value at some value, gives us our height of our rectangle. That is f of x right there. There's our functional value. This delta xk, this was our width of each of those subintervals. We are using dx, kind of like when we did derivatives. Dx, the change in x, delta x, you can see the connection there. Now, one of the problems with this limit definition, as we take the limit of n as n goes to infinity to the sigma, is it doesn't have our a and b in it. Now, our formula, I know, for delta xk was b minus a over n, so it's built into this, and then our c sub k was a plus k over delta xk. So the a and the b were built into that, but we write this here as the integral of a to b, so we can have what that interval is. So the way we read this is we will say the integral of a to b of f of x dx. And that integral means that limit. So if we go back to that example we looked at a second ago, here, this limit right here, if we wrote that as an integral, we would write it as the integral from 0 to 1 of 1 minus x squared dx. So that is a shorthand notation that means all of this on the other page. Doing all of that with the delta xk to ck and finding that limit, that's what this integral means. And for the homework today, that's kind of what we want to look at, the first part of it. We're going to be given one of these limits of a Riemann sum, and we're asked to write the definite integral. First off, you need the integral from 1 to 5. So we write the interval from 1 to 5. This part in here is our f of ck. So we're going to rewrite that as just f of x. So that would be 4x squared plus x. And then this delta xk we're going to write as just dx. So on your homework, the first couple problems are just taking this limit and writing it as this integral. Now, as we come back tomorrow and continue with this section, we will then say, what happens if we're given this integral and we want to evaluate it? What we're going to do there is tomorrow, or the rest of the homework you will see, is we will take this integral and we will write it as a limit of the Riemann sum to evaluate it, like we did over here. So we will do some more examples of these tomorrow of how to evaluate this integral using the limit of a Riemann sum. But that will be tomorrow's video.